Good afternoon, students. In today's GATE class, we will see uh, electrical and electronics measurements. In that, we will discuss instrument transformers. So generally, we know the term transformer. So transformer means it is a static device which transfers the power or energy from one circuit to other without changing the frequency by electromagnetic induction principle. That is mutual induction principle. So in DC circuits, to measure high currents or large currents, usually low range ammeters with suitable shunts are used. Okay, suitable shunts means that is suitable parallel resistances are used. Similarly, to measure high voltages, low range voltmeters with high resistance connected in series with them are generally used. So to measure large or high currents in DC circuits, usually low range ammeters with suitable resistances. Shunts means that is resistances connected in parallel are used. Similarly, to measure high voltages, low range voltmeters with high resistance connected in series with them are used. Generally, this method is neither convenient nor practical for alternating current and voltage instruments. It is generally suitable for DC circuits only. For alternating current and voltage instruments, this method is neither convenient nor practical. So for this purpose only, specially constructed accurate ratio instrument transformers are employed in conjunction with standard low range AC instruments. So their purpose is to reduce the line current or supply voltage to a value small enough to be easily measured with meters of moderate size and capacity. Okay, so by using moderate size and capacity meters, this method is suitable. So to reduce the line current or supply voltage to a small value. And generally they are used for extending the range of AC ammeters and voltmeters. Inherently, there are two basic advantages in this method using instrument transformers for the measurement purposes. So what are the two basic advantages means? First one is standard rated instruments may be used. Okay. So we can use the standard rated instruments for measurement purpose. Second one is operating personnel coming in contact with the instruments are not subjected to high voltage and current of the lines. So there is less danger to them. So persons who are handling this instrument, they are not affecting this high voltage and high current of the lines. So these are the two basic advantages inherent in the method using the instrument transformers for measurement purpose. Even with a low voltage system, these instrument transformers are used for measuring large currents so that heavy loads to the instrument panel and to the ammeter and other terminals are avoided. The operating principles of this instrument transformer is fundamentally the same as that of the power transformer. So generally we know the power transformer operating principle. The same concept or the same principle only apply in instrument transformers also there. Now we will see the classification or types of instrument transformers. So actually there are two types of instrument transformers. First one is current transformers, second one is potential transformers. So current transformers, in short form it is called as CT. Potential transformers, in short form it is called as PT. So current transformers are used for the measurement of current and the potential transformers are mainly used for the measurement of voltage. So instrument transformers extensively or highly used for precise or accurate measurements. These instrument transformers are widely used in protection circuits of power systems for the operation of various types of relays like over current relays, over voltage relays, under voltage relays, earth fault relays, and similarly there are various other types of relays also. These instrument transformers are mainly used. So these are the wiring diagrams of our current and potential instrument transformers. So in current transformers, there is a primary winding which is connected in series with the line, and also there is the secondary winding is connected to the ammeter. The potential transformer is connected across the line, and the primary winding is connected to the across the lines and the secondary winding is connected to the voltmeter. So these are the wiring diagrams for current and potential instrument transformers. So there are some merits or advantages of instrument transformers. So the advantages of the instrument transformers as compared with the ammeter shunts and the voltage multipliers are: first one, it enables the single range instruments to cover a large current or voltage range. So it enables the single range instrument which covers a large current or voltage range. So the normally the current ranges are 0 to 5 amps and the voltage ranges are 0 to 110 volt. And the second advantage is it is possible to locate the measuring instruments far away from the high voltage circuit by using long leads connecting the instrument transformer to the instrument. And third advantage is when instruments are employed in conjunction with the instrument transformers, the readings do not depend upon the constants. Constant means like resistance, inductance, and capacitance. That is R, L, and C, as in the case of shunts and multipliers. Next, many instruments can be operated from a single instrument transformer. So by using this single instrument transformer, many instruments or more instruments can be operated. This is fourth advantage. And fifth advantage is small power loss. So the power loss in the instrument transformer is very low. And the next one is sixth one is by employing current transformer with a suitable split and hinged core upon which the secondary winding is wound. The current in a heavy current bus bar can be measured without breaking the current circuit. That is one advantage. So by employing current transformer with a suitable split and hinged core upon which the secondary winding is wound, the current in a so the current in a heavy current bus bar can be measured without breaking the current circuit. And the disadvantages of the instrument transformers are demerits of the instrument transformers are: first one is it cannot be used for DC measurements. That is, it can be only used for the AC measurements. That is, it can be voltages to measure AC voltages and AC currents. It cannot be used for DC measurements. That is the first disadvantage or first drawbacks or demerits. Next, in using instrument transformers for current or voltage measurements, the ratio of primary current or the primary voltage to the secondary current or the secondary voltage is important. So this ratios gives the multiplying factor for finding the primary values from the instrument readings on the secondary side. Next, before discussing the current transformer and the potential transformer construction and working principle, now let us discuss the various terms which is relating to the instrument transformers. First term is burden of an instrument transformer. Okay, what is meant by burden of an instrument transformer? The load across the secondary winding can be conveniently expressed as the output in volt ampere at the rated secondary voltage. The rated burden is the volt ampere loading, which is permissible without errors exceeding the limits for the particular class of accuracy. So the total secondary burden is square of the secondary winding induced voltage divided by impedance of the secondary winding circuit including impedance of secondary winding. That is a secondary winding current square into impedance of the secondary winding circuit including secondary winding. So this is the formula or expression for the total secondary burden. So square of the secondary winding induced voltage to the impedance of the secondary winding circuit including impedance of the secondary winding. Otherwise, we can tell square of the secondary winding current into impedance of secondary winding circuit including secondary winding. Next, secondary winding burden due to load. Okay. So due to load, what is the secondary winding burden means? It is the ratio of square of the secondary winding terminal voltage to the impedance of load on secondary winding. Otherwise, we can tell in another way also, that is the square of the secondary winding current into impedance of the load in the secondary winding circuit. So this is the secondary winding. So next, transformation ratio. So it is called as the actual transformation ratio, which is denoted by the symbol KACT. So the transformation ratio is defined as the ratio of the primary phasor to the secondary phasor. Okay. So it is denoted by the symbol KACT. So it is the ratio of the primary phasor to the secondary phasor. That is the second important terms. So the transformer ratio, that is the actual transformer ratio KACT equal to primary winding current, that is actual primary winding current to the actual secondary winding current for a current transformer. Similarly, for a potential transformer, the ratio of primary winding voltage to the secondary winding voltage, both are actual. So this is the transformer ratio, actual transformer ratio. And the third one is nominal transformation ratio. It is denoted by the symbol KNOM. So nominal transformation ratio means it is defined as the ratio of rated primary winding current or voltage to the rated secondary winding current or voltage. So for a current transformer, nominal transformation ratio is nothing but rated primary winding current divided by rated secondary winding current. Similarly, for a potential transformer, it is the ratio of rated primary winding voltage to the rated secondary winding voltage. Our next important term is turns ratio. Turns ratio is denoted by or represented by the symbol K suffix T. So turns ratio KT for current transformer is, it is the ratio of number of turns of the secondary winding to the number of turns of the primary winding. Similarly, for potential transformer, turns ratio is, it can be defined as the ratio of the number of turns of the primary winding to the number of turns of the secondary winding. Normally, nominal transformation ratio is equal to the actual this turns ratio, that is K norm is equal to KT. Next, ratio correction factor. In short form, it is called as RCF. So ratio correction factor means it is the ratio of actual transformation to the nominal ratio. That is, it can be defined as the transformation ratio, that is actual transformation ratio divided by the nominal ratio, that is RCF equal to K ACT divided by K norm. So therefore, K ACT is equal to RCF into K norm. So the ratio marked on transformers is the nominal ratio. Now we will see the first type of instrument transformer, that is current transformer. First we will see the general aspects of the current transformer. So just as a shunt extends the range of a DC ammeter, so does the current transformer perform the same function as in AC circuits. So yeah, high magnitude alternating current can be easily measured by a combination of the current transformer and a low range ammeter. High magnitude alternating current can be easily measured by a combination of a current transformer and a low range ammeter. So here the primary of the current transformer consists of a few turns of thick cross section connected in series with the high current line. Very often the primary is just one turn formed by taking the line conductor through the secondary winding. Here the secondary winding consists of a large number of turns of fine wire designed for either 5 amps or 1 amps rating. So a current transformer is a step-up transformer. So the current transformer as a secondary effectively short circuited the low impedance of the ammeter. So this is the construction of current transformer. So here there is a conductor which carries the current, and there is the core which consists of the secondary winding of fine wire. So this is the current transformer connections. Okay. The diagram A is also the one type of current transformer connection. Similarly, B is also the current transformer connections. Okay. So the high voltage line is connected to the load through this current transformer. So in the above diagrams, the core material for CT is usually low loss silicon steel new metal. Okay. The core material used for the current transformer is usually low loss silicon steel. That is mu metal. Core should have high permeability and low losses. To keep losses low, flux density is kept low. So approximately the flux density is 0.1 Tesla. So we know that flux density means what? It is a flux per unit area. So this flux density is generally kept low, which is approximately or equal to 0.1 Tesla. The core lamination can be rectangular or ring shaped. A ring type core is jointly but difficult to wind. So windings must be rigid to withstand extremely large mechanical forces produced by short circuit currents. For low and medium voltages, tape and varnish insulations are generally used. While for high voltage working, current transformer may be compound filled or oil immersed. So the CT ratio is not equal to the ratio So the current transformer ratio is not equal to the ratio of secondary to the primary turns, mainly because of the effect of the magnetizing current. So the primary current can be thought of as the sum of the two currents. The first one is to balance secondary current so that primary primary and secondary MMFs may balance, and the second being the no load current I0. The component I0, besides being responsible for a slight error in the current ratio, which is also responsible for a phase angle error. The transformer must be carefully designed to minimize the ratio and phase angle error. Generally, the current transformer must never be operated on open circuit for the two reasons. What are the two reasons means? Two reasons means first one is there will be no secondary MMF, and since the primary current is fixed, the core flux will increase enormously. This will cause large eddy current and hysteresis losses, and the resulting high temperature may damage the insulation or even the core. This is the first reason that the current transformer must never be operated on open circuit. And the second reason is a very high voltage will be induced in the multi-turn secondary, and this high voltage may be dangerous both to life and to the insulation. So these are the two reasons that the CT or current transformer should never be operated on the open circuit. So this is the equivalent circuit of the current transformer. Similar to the ordinary power transformer, it is also consists of the, in primary side it has the resistance and reactance. So the primary winding resistance RP, secondary winding primary winding reactance is XP. And the no load component current can be divided into two component current. One is the core loss component current, another one is the magnetizing component current. And it has also the no load resistance and reactance, that is R0 and X0. EP is the EMF induced in the primary voltage, primary winding. VP is the voltage applied to the primary winding. And similarly, in a secondary side, ES is the EMF induced in the secondary winding. IS is the secondary winding current. RS is the secondary winding resistance. XS is the secondary winding reactance. The load consists of the resistance RE and reactance XE. And VS is the voltage across the secondary winding. So this is the equivalent circuit of the current transformer. Next, we will see the what are the various errors in the current transformer. So in current transformer, the value of transformation ratio, that is the actual ratio, is not equal to the turns ratio. Also, the value is not constant and it depends upon the magnetizing and the loss components of the exciting current, the secondary winding load current, and its power factor. This means the secondary winding current is not a constant fraction of the primary winding current, but it depends upon the above mentioned factors. That is exciting current, secondary winding load current, and its power factor. This introduces the considerable errors into the current measurements. In power measurements, due to the use of current transformer, two types of errors are introduced. What are the two types of errors means? First one is the ratio error. Second one is phase angle error. First we will see ratio error. Due to the actual transformation ratio, which is being different from the turns ratio, this ratio error occurred. The next one is phase angle error. Due to the secondary winding current, which is not being exactly 180 degree out of phase with the primary winding current, this phase angle error occurs. So these are the two types of errors which are introduced in power measurements by using current transformer. Next, we will see the characteristics of current transformers. So the performance of the current transformers under different operating conditions may be estimated or calculated by considering the phasor diagram. In that, first we will see effect of change in power factor of secondary burden. The power factor of the secondary circuit depends on the power factor of the burden on secondary. This directly affects the ratio error and the phase angle error. That is, the power factor of the secondary circuit depends on the power factor of the burden on secondary. This only affects the ratio and phase angle error. Next, effect of change in burden on secondary. An increase in the secondary winding circuit burden impedance means an increase in volt ampere rating. This necessitates an increase in the secondary winding induced voltage, which can be generated by an increased flux and flux density. So therefore, both magnetizing component and the loss component are increased. So subsequently, errors also increase. And the third one is effect of change in primary winding current. So when the primary current changes, the secondary current changes proportionately. At low values of primary current, the exciting current component and the loss component are a greater proportion of primary current, and therefore the errors are greater. When primary current increases, secondary current also increases, and there is a decrease in ratio error and the phase angle. Fourth one is effect of change in frequency. So the effect of change in frequency is similar to that produced by a decrease in secondary burden, as increase in frequency will produce a corresponding decrease in flux for the given EMF. Consequently, there is a reduction in magnetizing current and loss component current, and hence errors also get reduced. This is the effect of change in frequency. In current transformer, one more special type used, that is clip-on type current transformer. So the main feature or the special features of this clip-on type current transformer is it can be used instantaneously for measurement of current in a current carrying conductor, that is cable, insulated busbar or fuse link, without interrupting the circuit for connection of ammeter in series with the circuit. This is the main feature or special feature of clip-on type current transformer. So this is the schematic diagram of a clip-on type current transformer. So if you see the diagram, there is a current carrying conductor, which is the primary, and the secondary winding is connected on laminated hinged core. Okay, laminated hinged core. Here the trigger switch for splitting of core is mainly used here, and in that there is a black one, which is the place where the core is split. This is the schematic diagram of a clip-on type current transformer. So generally it consists of a laminated core, which is so arranged that it can be opened out at a hinged section by merely pressing a trigger-like projection. When the core is thus opened, it permits the admission of very heavy current carrying bus bars or feeders, whereupon the trigger is released and the core is tightly closed by a spring. So the current carrying conductor of feeder acts as a single turn primary, whereas the secondary is connected across the standard ammeter, conveniently mounted in the handle itself. So the ammeter gives the value of the current flowing through the conductor. So this instrument can be used in AC circuits only, and it can be operated by one hand. Okay. The accuracy claimed by the manufacturers is within 3% of full scale with the conductor in a central position in the core. So this is the various characteristics of current transformer. So far we have discussed the current transformer construction and operating principle and the characteristics. Next we will see the potential transformer construction and operation and its characteristics also. First we will see the general aspects of the potential transformer. A potential transformer is a step down transformer used along with a low range voltmeter for measuring a high voltage. So to measure high voltage, This potential transformer, it can be used with a low range voltmeter. So the primary is connected across the high voltage supply, and the secondary to the voltmeter or potential coil of the wattmeter. So since the voltmeter or the potential coil impedance is very high, the secondary current is very small, and the potential transformer behaves as an ordinary two-winding transformer operating on no load. So this is the potential transformer connections. Okay. So the primary winding is connected across the supply. So the secondary winding is connected to the low range voltmeter. So in the above diagram, the secondary is grounded. This is done so that if the insulation breaks down, the high voltage does not endanger personnel who may be reading the meters. Okay. So person who are reading the meters, they cannot affected by the high voltage if the insulation breaks down. So only the secondary is grounded in the above potential transformer connections. So these transformers are made with high quality iron core operating at very low flux densities so that the magnetizing current may be very small. Careful design ensures minimum variation of voltage ratio with load and minimum phase shift between input and output voltages. Potential transformer secondary is commonly designed for an output of 110 volt. So to obtain the output voltage of 110 volt, this potential transformer secondary is generally or commonly designed. This potential transformers, usually there are two types. One is the dry type and the second one is the oil immersed. Okay, first one up to the voltage of 5000 volt. Usually the potential transformers are of dry type, and between the voltage 5000 volt to 1,38,000 volt, either dry type or oil immersed type potential transformers can be used. Suppose if the voltage exceeds 1,38,000 volt means always immersed type potential transformers used. So these are the various types of potential transformers used. As a rule, the potential transformers are of shell type because such a construction develops a high degree of accuracy. Okay, this shell type potential transformer only mainly used to get high degree of accuracy, and this potential transformer is different from the power transformer. In power transformer, power transformer current is 5% of full load current, while in case of potential transformer secondary current is of the same order as magnetizing current. So the potential transformer has a small volt ampere ratings, that is we can say it is 15 volt ampere. Similarly, the primary and the secondary winding of the potential transformer are coaxial. Why means to reduce the leakage reactance to a minimum value. The low voltage winding, that is the secondary winding, is placed next to the core. Oil filled bushings are used for oil filled potential transformers to minimize the overall size of the transformer. When neither side of the line is at ground potential, two bushings are generally used. So this is the equivalent circuit of potential transformer. Similar to the current transformer, in potential transformer also there are so many parameters. In a primary side, Vp is the voltage applied to the primary winding. That is primary voltage, primary winding voltage. Ip is the current flowing through the primary winding. Rp is the primary winding resistance, and Xp is the primary winding reactance. I0 is the no load component current. This can be split into two currents. One is the IW and second one is IM. IM means magnetizing component current. IW means working component or no load loss component. Similarly, I0 consists of two parts. One is the R0 and X0. R0 is the resistance, no load component resistance, and X0 is the no load component reactance. EP is the EMF induced in the primary winding, and in secondary side, ES is the EMF induced in the secondary side, secondary winding. IS is the current flowing through the load, that is the secondary current flowing through the load. RS and XS. RS is the secondary winding resistance and XS is the secondary winding reactance. Load consists of resistance and reactance, that is RE and XC. VS is the voltage across the secondary winding or voltage across the load. Next we will see the characteristics of potential transformers. The errors, that is ratio and so first characteristics, effect of change in secondary burden. So with the increase in secondary burden, the secondary current is increased. So with the increase in secondary burden, the secondary current is increased, and consequently the primary current is increased. Both the primary and secondary voltage drops increase under the saw for a given value of primary winding voltage. There is a decrease in the value of the secondary voltage, and hence the actual ratio increases as the burden increases. So this variation of error is almost linear with change in burden. Further, the increased voltage drop, VP, that is primary winding voltage, advances while secondary voltage retards in phase. So as a result, the phase angle between the primary winding voltage and the secondary winding voltage reversed increases and becomes more negative as the current increases. Okay, so these are the effect of change in secondary burden in potential transformer. And the second characteristic is effect of power factor of secondary burden. So when the power factor of a secondary circuit burden is reduced, the angle increases. As a consequence, what will happen means current IP shift towards I0. The voltages VP and VS, that is primary winding voltage and secondary winding voltage, come more nearly into phase with EP and ES respectively, since the voltage drops are almost constant. So that results in an increase in VP relative to EP. But since VP is constant, therefore EP reduces relative to VP. VS also reduces related to ES. So the transformation ratio increases as the power factor of secondary burden reduces. So while VS advances in phase and VP retards, hence the negative phase angle reduces as a lagging power factor of the secondary decreases. So these are the second characteristics of the potential transformers. And the third one is the effect of change in frequency. Effect of change in frequency. So generally the flux is inversely proportional to the frequency for a constant voltage. So thus with increase in frequency, flux is reduced and therefore IM and IW, that is magnetizing component current and no load working component current, are decreased, leading to decrease in the voltage ratio. This decrease is not so much with increase in frequency, and the leakage reactance increases. Therefore, leakage reactance drops are increased, giving an increase in the ratio. Thus, changes in the voltage ratio are dependent upon relative values of IA and leakage reactances. So with the increase in frequency, the phase angle is increased since both the effects advance VS, and the increase in secondary reactance retards VS. So these are the various terms which is related to the effect of change in frequency. And next we will see the fourth characteristics, that is effect of primary voltage. So the variations of errors due to change in primary voltage are of no importance as the supply voltages do not vary widely. So this is the fourth characteristics of potential transformers. Next we will see Reduction of errors in instrument transformers. The errors, that is ratio error and phase angle error in instrument transformer, may be reduced by using the following methods. First method is reduction of magnetizing and loss components. Okay, that is of exciting current I naught. So in that first one, from there will be some equations in the ratio and phase angle errors. So from the equations of ratio and phase angle errors, the errors depends on Im and Iw. That is which are the components of I naught. So these components can be reduced. That is Im and Iw can be reduced by first one, by using materials of high permeability. By using high permeability materials, we can reduce Im and Iw. Similarly, keeping the flux density in the core to low value. Second one is, in the core there will be the flux density. So by keeping the flux density in the core to low value, we can reduce the Im and Iw. Third one is choosing low reactance score. Okay, if we choose the low reactance score in instrument transformer, Im and Iw can be reduced. Next, using a core of large cross section. Okay, using the core of large or high cross section, we can reduce the errors, okay, due to Im and Iw. Next one, providing smaller magnetic paths to the flux. By providing smaller magnetic paths to the flux, we can reduce Im and Iw component. Next one, designing the assembly and interleaving the core with proper precautions. So these are the various methods of reduction of magnetizing and loss components of the exciting current I naught. And second method is reduction of resistance and leakage reactance. Okay, reduction or decrease of resistance and leakage reactance. The errors depends on the voltage drops, which in turn depends on the values of resistance and leakage reactance. So the resistance can be reduced by using thick conductors, that is a large cross section conductors, and using the smallest length of mean turn. This is the first method. And second, the leakage reactance of the windings depends on upon the leakage fluxes of primary and secondary windings, and therefore windings must be kept as close as possible. Further, high flux density means high flux in the core. So the windings have less number of turns, which obviously results in smaller leakage reactance of the windings. So this is the second method of reduction of errors in instrument transformers. That is a reduction of resistance and leakage reactance. And the third one is the turns compensation at no load. That is when IS is equal to 0, the actual ratio, that is K act. In case of primary transformer, in case of potential transformer, which exceeds the turns ratio KT by an amount IWRP plus IMXP divided by VS. Okay, actually this is the equation which comes from the equivalent circuit simplification. So the ratio further increases with an inductive or resistive load because of voltage drops in resistance and the leakage reactance of the windings. If KT is equal to K now, the K act differs from the nominal ratio under the errors creep in. So the remedy lies in making the KT less K now. This can be accomplished by either reducing the number of turns of primary winding or increase the number of secondary winding turns. By doing so, it becomes possible to make the actual ratio K act equal to the K norm. That is, actual ratio is equal to the nominal ratio for one particular value of burden. At the same time, there is a general reduction in the ratio error over the entire working range of the burden. So this is called as what? Turns compensation. So the phase angle theta practically remains unaffected due to a small change in KT. Now let us see the comparison of current transformers and potential transformers. Okay. So in current transformers, the generally must always be shorted. But in potential transformers, the secondary is nearly under open circuit condition. This is the first comparison. In a current transformer, the secondary must always be shorted. In potential transformer, secondary is nearly under open circuit conditions. And the second difference is in current transformer, the winding carries full line current. The winding carries full line current in current transformer. But in potential transformer, the winding is impressed with full line voltage. Okay. The winding is impressed with full line voltage in potential transformer. And the third difference or third comparison is the primary current is independent of the secondary circuit conditions. But in potential transformer, the primary current depends on the secondary circuit conditions. Next, fourth difference, this current transformer can be treated as series transformer under short circuit conditions. Similarly, in potential transformer, this potential transformer can be treated as parallel transformer under open circuit secondary. Next, fifth difference is, in current transformer, a small voltage exists across its terminals as connected in series. But in potential transformer, full line voltage appears across its terminals. Last difference is, in current transformer, the primary current and the excitation varies over a wide range. But in potential transformer, the line voltage is almost constant, hence exciting current and the flux density varies over a limited range. So these are the various differences of current transformer and potential transformers. Actually, in both current transformer as well as the potential transformer, we are calculating the ratio error. So in potential transformer, the ratio error or the ratio voltage error can be calculated by using the formula. That is, the actual ratio of transformation varies with the operating conditions and the error in the secondary voltage, which may be defined as the percentage ratio error equal to K norm minus K act divided by K act into 100. So this is the percentage ratio error formula or expression. So percentage ratio error formula or expression is K norm minus K act divided by K act into 100. Similarly, in a current transformer, the ratio error can be calculated by the formula percentage ratio error equal to nominal ratio minus actual ratio divided by actual ratio into 100. So this is the formula or expression to calculate the percentage ratio error in current transformer. Nominal ratio minus actual ratio divided by actual ratio into 100. Next, the phase angle error can be calculated in current transformer by using the formula or expression is phase angle error theta equal to 180 degree divided by pi into Im cos del minus Iw sin del divided by kt into Is degrees. Actually, this is the formula which is derived by using equivalent circuit of the current transformer. So the phase angle error in the current transformer can be calculated by this formula theta equal to 180 degree divided by pi into Im cos del minus Im sin del divided by kt into Is degrees. We can calculate the approximate formula for errors. So by using approximate formula, the phase angle errors can be calculated by theta equal to 180 divided by pi into Im divided by Ip. This is the approximate formula for calculating the phase angle error in the current transformer. So actually, by using equivalent circuit and phasor diagram, this ratio error and phase angle error formula can be obtained in both current transformer as well as potential transformer. Okay, students, that's all. So this is the These are the various topics which we have discussed in today's GATE class. Okay, today's we have discussed in instrument transformers. In that we have discussed the construction and operating principles and various characteristics and how to reduce the errors in instrument transformers, and we have discussed the comparison between the potential transformer and current transformer. In the next class we will discuss the next topic in electric and electronic measurements. That's all.